Running a little late, so we'll start this session. I am the chair of this session, and with the permission of this chair, I'm taking 2 minutes to tell you a story. I've taken the permission of the chair for 2 minutes. Okay. And this story is from 31 years ago, so many of you are probably not born at that time. This was when one well-known Indian physicist was visiting Europe, and he wrote to Professor Leutwiler of the University of Bern, saying that he would like to visit, give a talk, interact with people in the department. And Professor Leutwiler wrote him a reply saying, yes, you're welcome. Come and spend 3 days in Bern. We'll take care of your local expenses. But please don't give a talk. We don't want you to give all your crazy ideas out to our students and postdocs. We don't want you to corrupt them. And so that is what Leutwiler said. And I remembered it because the same thing happened with me, because I registered for this conference and I asked Sudhir if I can give a talk. I'm sorry, Professor Vempati. And he said, absolutely not. I don't want you to put all these crazy ideas in front of a very young audience here. So I pleaded and I begged, and finally he allowed me to chair this session. So here I am. Okay. Actually, I'm very happy that I can contribute in this small way. Thank you, Professor Vempati. Anyway, so we have some very interesting talks coming up in this session. The first 2 talks are one by Bhavesh Chauhan from BITS Pilani, and following that, Tanmay Modak from ICER Behrampur. Tanmay Modak is going to give a talk on future experiments and how they are going to probe inflationary landscape. That will be the second talk. The first talk by Bhavesh Chauhan is about the coolest thing on earth, the IceCube experiment, and he's going to talk about. This is always a problem. Cosmic sterile. How do you say this? Either you say it as cosmic sterile neutrino. No, you don't say it like that. You say cosmic sterile neutrino. So sterile hangs with neutrino, and then you add cosmic as an adjective. Anyway, so cosmic sterile neutrinos, Bhavesh Chauhan. Sorry I took so much of your time.
Okay, so let me begin by thanking the organizers for having me here. So today I will talk about probing the cosmic sterile neutrino background with the IceCube detector. So, in the last decade or so, since IceCube has been collecting data, it has done some wonderful things, right? From the first observation of PeV neutrinos to identifying sources where the TeV energy neutrinos are coming from, to recently observing the Glashow resonance event. Right, so IceCube has been doing some wonderful things, and most of the results that IceCube present is actually consistent with the expectation of a diffuse astrophysical neutrino background, which is characterized as a single power law. So basically, you have there are 2 free parameters. One is the overall normalization scale of the flux, and the other thing is the spectral index. Right, so IceCube has been seeing these kind of neutrinos for last 10 years, and in this talk we'll focus on 3 different data sets. So the first one is the recent 7.5 years high energy starting events data set, the HESE data set. These are events which start inside the detector volume, so you have very good understanding of the energy of these detectors, of these events. The other is the 9.5 year through-going muon tracks from the northern hemisphere, which is very mouthful, so I'm going to call it northern tracks. Right? In literature, you can also see that sometimes it's called as EHENTs, extremely high energy northern tracks. And the other data set that we are looking at is the 4.5 year PeV energy partially contained events. This is the PEPE data set, and the Glashow resonance event was observed in this set. So one of the key difference between this and the Hesse dataset is that since you're looking at very high energy events, which are very rare, you can actually increase the detector volume. You don't need to see fully contained events. So the detector volume is larger, but then the exposure is smaller. So it's only it's nearly half the exposure of Hesse datasets.
That doesn't contain PEV.
This one does not have, this is, the Glashow resonance event is actually a surface event. So the fiducial volume for high energy starting events is smaller, so this doesn't have that. I'll come to that. So the event, it's from 60 TeV to 10 PeV. That's the range. Good. So I would like to motivate a small hint of discrepancy. This is a very small discrepancy, probably not very exciting for a lot of people, but I found it interesting. So the spectral index that is inferred from the Hesse dataset and the spectral index that is inferred from the northern tracks seems to be around 2.5 sigma apart. And this is just a cartoon picture of what that discrepancy actually looks like. So, but this is in log scale. So this is the kind of this is the discrepancy that we try to solve in this work. So what's the motivation? So this is the high energy. So this is the Hesse data, the Hesse events that IceCube has observed. Below 60 TeV, there is large number of events coming from atmospheric backgrounds. So the analysis is from 60 TeV to up to a few PeVs. Right? So there are two possible solutions. One is this blue curve, which is the standard fit from IceCube. In this fit, you actually explain the low energy events very well, and the PeV energy events seems like a small aberration. And a lot of papers have been written about this PeV bump, if you would like to call it. Maybe these PeV neutrinos are coming from decay of a PeV scale dark matter, or maybe the cross section is not the standard model cross sections, and maybe there are beyond standard model resonances. For example, we heard about R parity violating supersymmetry today. The leptons and squarks in R parity violating supersymmetry can actually produce a resonant behavior just like Glashow resonance and give you an additional bump here. Similarly, leptoquarks, if somebody is interested. One of the problems that I feel about this kind of an explanation is that the observation of Glashow resonance, which is just one event, seems to be in conflict with this kind of an explanation. So we think of another possibility where the spectral index is slightly smaller, but now you explain the Glashow resonance event, the PeV events, also the low energy events. In this case, over here in between like 300 to 800 TeV, there seems to be a lack of events, and this lack of events would come if there is a dip in the astrophysical neutrino spectrum, right? So why would there be a dip in the astrophysical neutrino spectrum? Well, if the neutrinos that are produced, let's say in sources which are far away, at least a few megaparsecs, then if during the propagation they can interact with something in the background, right? And if it produces a mediator on shell, which is basically a resonant production, then there is this cross section is like a resonance cross section. So this is very narrow, and then you can have a absorption feature which is very narrow. So contrary to if you have a T channel exchange, you'll have a very broad feature. So if you have an S channel exchange, then there is a possibility of having a narrow absorption feature which is limited to 300 to 800 TeV. Great. So the flux, this is the differential flux, is solved by, we obtain the differential flux by solving this differential equation, which has, this is the Boltzmann transport equation, which has 4 components. First is the expansion due to universe, because these neutrinos are coming from large redshifts, so there is expansion. The source, I mean, what is the source of these neutrinos? We don't know, so we model it as proportional to the star formation rate. And then there's this attenuation which comes from this interaction, and then there is regeneration. Regeneration is reappearance of neutrinos in the final state with lower energies, right? So we solve this equation for our case. So the question is, what background are you talking about, right? So this can be any background that you all like. For example, if you like dark matter, have neutrino dark matter interactions. A very popular choice is to have active neutrinos, but in this work we'll talk about the background being sterile neutrinos. So why do we expect that there is a sterile neutrino background? Well, the jury is still out whether a light sterile neutrino exists or not. There are evidences in favor of and against the existence of sterile neutrino. But one thing that is very clear is that if you have a fully thermalized sterile neutrino, then you are in conflict with cosmology, right? The measurement of BBN n effective is incompatible with having a fully thermalized sterile neutrino. So this problem was partially resolved like a few years back when they proposed that if the sterile neutrino is self-interacting, then akin to a MSW kind of effect, you can delay the production of sterile neutrinos, and because this is a delayed production, you get rid of the BBN bounds. So this is a very popular solution to escaping the cosmology bounds for sterile neutrinos. There are some problems and in this resolution which still require some clever resolutions, and I can talk about it offline if you want. But the key point is, because the neutrinos recouple later on, they are produced from the active neutrinos, so you expect a cosmic sterile neutrino background along with a cosmic active neutrino background, right? This is not possible if the sterile neutrino decays, for which you need some additional physics. So we'll work in the minimal physics example where there is no sterile neutrino decay. Good. So simply I'll just introduce what is the BSM Lagrangian that we are thinking of. It's just sterile neutrinos interacting via a vector mediator. The other possibility is to have a pseudo-scalar mediator, but we find that there are strong constraints from meson decays which are avoided if you have a vector boson mediator because of unitarity. So to get rid of the meson bounds, we use the model proposed by Basu and Kopp, where the mediator is a vector mediator. So we use this new prop. It's a public package to solve the transport equation, and we have modified it to include 4 flavors. And we also use the public Monte Carlo simulation that is provided by IceCube to generate the event spectrum. This is a slightly better way to estimate number of events than just using effective areas, because this approach takes care of a lot of detector systematics as well, right? Good. We also use this code to actually calculate the likelihood function, and these are our main results. So in the parameter space of the sterile neutrino mass and the gauge boson mass, which are the 2 free parameters of our model, we find that there is a mild preference as opposed to this point where there are no dips. We find a mild preference for having a dip between 300 to 800 TeV. Our result also shows us a small island which we call the NSI island. This is the island where you have the sterile neutrino mass. This is agnostic to the mass of the sterile neutrino. It's so low, the gauge boson mass is so low that the dip from the sterile neutrino is beyond the Hesse fit, which is basically less than 60 TeV. So this is the dip. This is the parameter space for which you'll have active neutrinos giving you the dip between 300 to 800 TeV. So the best fit comparison between the Hesse best fit, the Hesse best fit and our work. This is what the flux would look like. You can see that it marginally explains Glashow resonance better than the Hesse fit. And in the event spectrum, you can see that our best fit result gives you the necessary features, I mean, if you think of these as features, the dip in the spectrum can actually produce some of these aberrations. But note that this is a log scale in events, so this is kind of scaled. So you don't really have that strong of evidence for these features. The more important result, I would say, is that by including these features, we are able to conclude that we are able to infer a spectral index which is slightly lower than what the spectral index you would infer from the standard single power law fit. And we see that the inclusion of these dips in the spectrum actually makes the result slightly more compatible with the spectral index that is inferred from northern tracks. So this is one of the main results of our paper. Good. So topically, I thought I'll give you a small picture of what is going on. In this 100-meter race, it seems that everything is a very good fit. You actually need a longer race to distinguish between these explanations of what is going on. So we ask ourselves, well, whether if IceCube Gen 2, which is an upgrade of IceCube, which has roughly 10 times the more exposure, whether that can actually give you a better resolution, whether a single power law or a single power law with dips is a better fit to the data. So this is our forecast, and it seems unlikely. Even with 25 years of data, what we see is only increase in local significance. But what we are hopeful for is that there are many other experiments, like for example KM3net, which are very IceCube-like, and if these features are real, then KM3net-like experiments should also see some of these absorption features. Right. So with this, I kind of conclude that introducing a dip in this astrophysical neutrino spectrum makes the Hesse data set compatible with what you get from northern tracks. We have considered the dip to originate from a sterile neutrino. It's not necessary. It could be from any favorite model of yours. And with this current data, right now, there is a large overlap between the two solutions. But with more data, we hope that this would be resolved. Yeah, so that's all. Thank you.
Thank you, Bhavesh. Thank you for finishing early. Like one of those people running. Anyway, sir, do you have time for a couple of questions?
Yeah.
Okay, very good.
Thanks, Bhavesh, for the nice talk. I know it's a phenomenological work, but it's probably a thing. I mean, you are coupling a vector particle to the sterile neutrino. You may run into anomalies if you. Yeah. So I think that whereas if you make the vector into a scalar, everything is fine. So yeah. your phenomenology will not change at all.
Yeah, that's a very good point.
Probably using a scalar is a bit better.
So there is an answer to that as well.
Oh yeah. Any comments? Yeah.
No. So one of the so this kind of a model runs into the sum over mu constraints, and one of the resolutions for avoiding those constraints is to have additional light sterile neutrino species. So if we include one more sterile neutrino, which is light, the absorption feature would be much at very high energies, which you don't see, and it gets rid of the anomaly as well.
But then you have actually NET or something.
Yeah. If we gauge it, then we can add one more sterile neutrino, which makes it consistent.
Yeah, but then you have a prediction at higher energies immediately, right? If it's a vector, you can differentiate a vector from a scalar using this, right?
Yeah. I mean, if we have events at high energies, we should be able to.
Okay. Thanks. Thank you.
Yeah. Yeah, so one of the strongest constraints that still remain on sterile neutrinos even after including this is the sum over neutrino mass constraint from CMB. That seems like, yeah, but there are clever resolution, as I said, adding some light degrees of freedom. Also, all of these constraints depend on the assumption of lambda CDM. So the moment you relax that, some of these constraints are also relaxed. So I have not considered any oscillation constraints. because in oscillations this picture is not clear, right? There are some signals, there are some constraints.
What stops you this extra particle? Yeah. Meaning, when you gauge it, what stops it to interact with other active neutrinos?
It does not actually.
It should not. Yeah.
It does not. Sorry. So this is the dip because of interaction with the sterile neutrino background, and this is the dip because of the active neutrino background. So it does induce.
So it does induce some NSA effects.
Yes, and that is exactly what you see in this island I was talking about.
Okay.
Yeah, this island is this NSII, this non-standard interactions or neutrino secret interactions island, which are also induced by this.
Let's move on to the next talk. Before that, we thank Bhavesh again.